Okay, so very much. I want to thank the organizers for this wonderful conference. I learned a lot of geometry and for the opportunity to present this joint work with Daria Poliakova on scaffolding projection. I want to build something, so I guess the first thing I have to do is to give you the plan. So maybe I start really from scratch and I remind you what is a lattice, or maybe a complete lattice. Complete lattice, so it's a poset where any subset has a mid and a joint, so a greatest lower bound and a least upper bound. And when you know a lot of examples of lattices, Boolean lattice, distributive lattice, so inclusion poset of other ideas of a poset, or the dominance lattice on Rn. I will illustrate the talk with two special lattices that we like a lot. So on the left, you have the weak order on permutations of 1n. And on the right, you have the Thematic lattice on binary trees with n internal nodes. So let me remind you the cover relations in this poset. So on the left, they correspond to transposition of consecutive letters. And on the right, they correspond to right rotations. Okay? And this poset, or the Hasse diagrams of this poset, turn out to be skeleta of, or directed skeleta of polytopes on the left of the permutahedron, on the right of the associahedron. I will not use at all geometry for polytopes in this talk, but a lot of posets or lattices that I will consider come from polytopes. Okay, and I will use these two examples of lattices to try to tell you a little bit of techniques to prove that a given poset is a lattice. Okay, so a priori you have to suffer and just take a subset and try to prove that it has a joint and a root. Okay, so I will essentially, I will focus in this talk only on finite lattices, so I only have to check this for pairs of elements. And if my poset is finite and has a minimal element, then I can just focus on the joint and the meet will be automatic. Okay, so I just need to do half of the work. And there is also a very important lemma, which says that it is enough to check existence of the joint for x and y that covers the same element. Okay, so this is called the BZ lemma for Björner, Edelman, and Ziegler. It's a very important lemma. It really simplifies a lot of things. There is actually a whole industry of BZ type lemma in Reading's survey. Okay, so that's when you have, that's when you try to prove that you have a lattice from scratch. You also have other approaches, meaning using another lattice to prove that your poset is a lattice. So one thing that you can do is try to embed your poset in a non-lattice. I will show you what I mean by that. Or you can try to see your poset as a lattice or semi-lattice or quasi-lattice quotient of a non-lattice. Or you can, I also mentioned that because it's sort of related to what I do. You can try to construct your poset P by iterative doublings of order convex sets, or even better, intervals. So interval doublings, the construction of Day. I will not explain you exactly what it is, but this is an iterative construction, and we'll also do an iterative construction. I don't really think that it is really related, but at least the idea of using iterations. Okay, so maybe let me show you what I mean by embed P in a non-lattice. So if you have a lattice L, and you have a closure operator on L, so it satisfies the three conditions, then the set of closed sets is again a lattice. Okay, so for example, if you have a vector space and you look at the subspaces of your vector space, then it will form a lattice because it's a set of closed sets under the closure operator, which is a span. Okay, so same with these other examples. And I want to use this idea, it's not exactly the same, but almost, to prove you that the weak order is a lattice. Okay. What do I do? So I presented the weak order in terms of cover relations, but you know that you can also define the weak order by inclusion of inversion sets. And now, instead of thinking about permutations, you can try to think about inversion sets and understand why these inversion sets form a lattice. So first thing that you do, you try to understand what are inversion sets. And these are precisely transitive and co-transitive sets, or some people would say biclosed sets. Okay. And then you just show or observe that the join, or the, let me say the sentence, the inversion set of the join of two permutations is a transitive closure of the union of the inversion sets of the two permutations. Okay, so you understand the join directly on inversion sets, and then you know that you have join, your poset is finite, bounded, so you have a lattice. Okay, so that's probably one of the shortest proofs that the weak order on permutations is a lattice. Okay, so second technique, you try to see your poset as a lattice quotient of a non-lattice. So the lattice quotient, you start from a lattice congruence, which is an equivalence relation which respects midths and joints. And if you have something like this, then you can define automatically a quotient lattice on the equivalence classes of your congruence. And this is a good example, a good technique to prove that the Thematic lattice is a lattice. Namely, you see it as a lattice quotient of the weak order by the so-called Sylvester congruence. So there are several ways to define it. Let me show you the fastest way to define it. So what I will do is that I will have a congruence with one equivalence class for each binary tree. So I tell you now the opposite. I start from a binary tree and I will tell you what is the equivalence class. Okay? So I start from a binary tree. I label the vertices of this binary tree in order. So it means I go around my tree. And each time I pass below a vertex, I write a number. And then I think of this binary tree as a poset from bottom to top. And now the linear extensions of this poset are precisely the permutations that I put in this class. Okay? And you can prove that you obtain this way all permutations. So it's indeed an equivalence relation. And it is indeed a congruence. You can also check that. And the quotient of the weak order by this congruence is the Thematic lattice. So that's a very important way to prove that the Thematic lattice. Okay, so using these techniques, in algebraic combinatorics, there are a lot of proofs that things are lattices. Of course, this list is in no way exhaustive. You will see that I made my choice in a certain way. So in this list, at the beginning, you have lattice quotients, in particular the work of Nathan Reading. So the Carbian lattices, rectangulation lattices actually come in two ways. Permitry and brick lattices are also lattice quotients of the weak order. Then you have interval hypergraphic lattices, which are not really lattice quotients of the weak order. They are quasi-lattice quotients of the weak order. It's a little difference with what I presented. There are the non-piercing lattices, which are proved to be lattices, or the non-piercing lattices of Jantel algebras. So there are also lattices of torsion classes of Jantel algebras. And we prove, one way to prove that are lattices is to obtain them as lattice quotients of something which looks like the weak order. And the other three families of lattices here are not of that kind, or at least not the type that I know of. And some of them were proved really using the BZ lemma. Okay. So now I can tell you the plan of the talk. So the plan is to start from this lively activity on lattices, okay, and to replace it by something automatical. But I'm not super sure that I'm happy myself with this paper. It really simplifies a lot some papers that I was really proud of. But I hope that at some point we will manage to join originality and this technical proof to the music. Okay, questions so far? Oh. Okay, so I want to speak about scaffolding projection, and I will start with the baby version of that, which are ladder projection. So what is a ladder projection? Here's the definition. So I want a projection, a map file from a poset P to poset Q, which has these three properties. So the first thing is that it has to be order preserving. So that means that if P is smaller than P prime, then pi of P is smaller than pi of P prime. Then the main condition is L2. So I want that the fiber of any element in Q is a finite chain whose maximum I call T of Q. Okay, so that's the main condition and the reason why I call it ladder. Okay, and I want this map T to be order preserved. Okay, so that's three conditions of the ladder projection. So here are two examples of ladder projection. On the left you have P, on the right you have Q, and you should see that. So here's the projection forgets the last coordinate, and the fibers are in red. Okay, so fibers are chains. Can you spot the difference between the two pictures? So my 7-year-old told me that this edge is on the left, while that edge is on the right, but I expect more from you. So top one is a lattice and the bottom one is not. Okay, so in the bottom picture, these two blue elements have no join and these two red elements have no meet. Okay, so now I want to explain you what I want to do. I will start with a poset, will be P, and I want to prove that it's a lattice. What I will do is that I will find a certain projection where Q is a lattice, and I will hope that I'm able to pull back this lattice property. Of course, it's not always the case. We already have an example where it's not always the case. We'll try to understand a sufficient condition for it to be the case. What is certainly true is that if you have a ladder projection and P is a joint semilattice and Q is a joint semilattice, this is very easy to do. Let me show you how it works. So you want to compute the join of two elements in Q. Well, you can just pull them back to their top, the top of their fiber. Then you compute the join of the top of the fiber and you push it back. You push it there to Q, and you get here the join of what you started from. Okay, so that's its formula. And this is really the proof with 2 lines, but it's not the direction that interests us. So what I want is when is the reverse implication true. Okay. And for this, I have to define the transport maps. What is a transport map? So I start with Q smaller than Q prime in Q. And I define a map from the fiber of Q to the fiber of Q prime. What does it do? So if I start from P in the fiber of Q, then I want to go to the fiber of Q prime to be bigger than P, but to be minimal for this property. Okay, so I think of it as a transport. I try to push from the fiber where I am, the fiber of Q, to the fiber of Q prime, and I try to go as fast as possible because I'm in a hurry. Okay, these are the transport map in our 2 ladder projections. And I will say that the ladder projection is flat if the transport map compose properly. So if Q is smaller than Q prime, smaller than Q prime prime, so here blue, green, and red, I take an element P in the fiber of Q, then I can transport it to the fiber of Q prime, and then I can transport the result to the fiber of Q prime prime. And I want this to be exactly the same as if I had transported directly P to the fiber of Q prime prime. Okay, so you don't want to lose time by making a stopover. Okay. So on top it works, and on the bottom it does not. Right? So if I transport P to Q prime, and the result to Q prime prime obtains this element. But if I have transported P directly to Q prime prime, then I will have that element which is lower. Okay, so I lose time making this stopover. And the main theorem of this talk is that if you have a flat ladder projection and Q is a joint semilattice and P will be. Okay, so how does it work? You want to compute the join of 2 elements in P. Well, first thing you project them to Q, you compute the join there, and now you transport your 2 elements in P to the fiber of the join and take the maximum. So I wanted to show you the proof of that. I will flash it. So the first thing which we use, yes, go ahead.
So if P has a minimum, does this imply it's a lattice?
Yes, you said
Okay.
because yes, it is finite and has minimum. I mean, here I will have at the moment
does this work for infinite?
some words for infinite, but we are still writing the paper, so I don't want to put my hand on fire for that. But okay, which I will only speak about finite lattices. Okay, so I wanted to tell you just the ingredients of the proof. So the first ingredient is that you can use transport to understand comparison in P in terms of comparison in Q and comparison in fibers. Okay, so you can compare P and P prime in P by just comparing their projections, Q and Q prime, and comparing the transport of P to Q prime with respect to P prime. That's a lemma. The full proof is here. And then we use this lemma to prove the theorems that I told you. We don't go through the proof, but I promise you that all the proof is here. Okay? So just what I wanted to flash the proof because you can go to my webpage, look at the slide, and we'll have the proof. It's just a little check. Okay, so this is the main theorem of the talk, I would say. Maybe I should have called it a lemma. So here is the full setting. The problem with the slide talks is that you cannot go to the past, so I decided to do a broad slide. So this is the same slide. So that we have the setting here, and we will go back to this from time to time. Okay, any questions so far? Okay, so we go to applications of this ladder technique. And the first we'll do is a weak order. So weak order again, so inclusion of inversion sets permutation. And you know a very simple projection from the weak order on n elements to the weak order on n-1 element, which is just to take a permutation and erase n. Okay, that's a very natural permutation, very natural projection. And I claim that it is a flat ladder projection. So let me explain the color code here, because all pictures will look like this. So what I did here is that I colored the numbers from 1 to 4. Last one is red, and the 3 is green, and so on. And then I colored the edges according to the last number I had to erase. So I erased 4, then I erased 3, and so on. So that at the two endpoints of these edges, when I erase this number, I see the same thing. So for example, this edge is red, because if I erase 4, at both endpoints I see 1, 2, 3. This edge is green, because if I erase 4, I don't see the same thing, but if I erase 4 and 3, I see the same thing, and so on. Okay, is it clear? So in particular, the fibers of the map are the red paths. You should see that they are paths. Maybe I didn't do your life easy. It would have been easier if I drew the weak order this way. What is this representation of the weak order? It's called a cubical realization. So what I did is that I placed each permutation in 3 space at the coordinates are its lemma code. If you don't know what it is, it's not super important, but you have a way to do that. And if you do that, then the colors that I have here correspond to the coordinate lines in the cubical realization. Okay, so I want to show you, make you at least one proof that something is a flat ladder projection. So let's try to prove that this erasing the number n in the permutation is a ladder projection and it's flat. Okay, so we said weak order is inclusion of inversion sets. The projection is the division of n in sigma. In particular, you can just compute the inversion set of the projection in terms of the inversion set of sigma. And conversely, if I have a permutation tau, then the fiber will be, well, you just choose where you insert n in your permutation. And I will denote by tau insert I, the insertion of n at position I in tau. Okay? So this will be tau insert 4, tau insert 3, and so on. Okay? And you can also compute the inversion set of tau insert I in terms of the inversion set of tau. So now let's check that it is a ladder projection. Well, if sigma is smaller than sigma prime, then just by inversion set arguments, we already computed the inversion set of phi of sigma. You check that phi of sigma is smaller than phi of sigma prime. The important thing, the main property is the second property. So the chain, the fiber is a chain. It starts from you put n at the very end, so at position n, and then you move it forward until you reach position 1. In particular, the top is the insertion of n at position 1. And now this T map, the maximum, the top map, is clearly order preserving, because if tau is smaller than tau prime, you make some moves to go from tau to tau prime. You can do exactly the same moves ignoring the n at position 1, right? So you can also prove it using that, but it's completely okay, so now it's a ladder projection. I just have to show you that it's flat. So for that, what I do is that I guess and prove the formula for the transport. And then I show that this formula for the transport enables me to show that the transport is flat. Okay, so it's a flatness condition. So that's a lot of words, but I want to explain what happens. So what happens is that you can look at examples. So I have a permutation tau and a permutation tau prime in the projection, and I have something in the fiber of tau. So it's tau where I inserted n somewhere at position I. Let me call that sigma. So I have my permutation sigma, and what will happen is that it has So n is somewhere, and there are some numbers to the left of n. Okay, and whatever happened to these numbers, so these numbers in to prime might go to the. Sorry, I start again this way. So I have n somewhere, and you have some numbers to the right of n in sigma, and now these numbers can move to the left. Okay, and if they move to the left, well, they will push n because it's an inversion, right? So they push n. Okay, so the result of the transport is that you have to insert n to the left of the leftmost value in tau prime, which was to the right of n in tau. Okay, does that make sense? So the idea is that people push the tall guy to the left. Okay. So now in particular, imagine I have tau smaller than tau prime prime, and I transport a given permutation sigma from tau to tau prime. So someone push n. Okay, and now I look at what happens after. Well, some other people will push n. Maybe he will push n. What is sure is that whoever pushes n has not yet been exchanged with the last person who pushed n. Because I want tau prime prime to be bigger than tau prime. Okay, so whoever is pushing n was already to the right of n at the very beginning. And this shows that the transport is fast. Okay, so maybe you will not be convinced at the moment. It's quite a complicated proof that the weak order is a lattice with a very simple proof. But I promise you that soon we'll do much simpler proofs than what existed before. Any questions on this proof? Okay, so in particular, we showed proving that this projection is flat. We showed by induction that the weak order is a lattice. Okay, so now isosahedron. So I did exactly the same. Now my projection is that I erase the rightmost leaf. Okay, so I have a tree. And I'm not sure whether it's visible or not. I hope it's visible maybe on this one. I have a tree, and I color the leaves from right to left with the same color, red, green, and blue. And the projection consists in just erasing this last leaf. Okay, and I color the edges according to the same rule. So I color an edge with the last color I had to erase to see the same thing. For example, this one is red, because if I erase red, I hope you see that I see exactly the same tree. Okay. And this one is green, because if I erase red, I don't see the same thing. But if I erase red and green, I see the same thing. Okay. Okay. So again, here you see that the fibers correspond to the red path. Here it's even easier to see that they are paths. You will also see it easier if I had drawn the cubic realization of the isosahedron. So here it's the coordinates are given by the bracket vectors of Fung and Thematic. Okay, and again the colors correspond to the coordinate lines in 3 space. Okay, so again this projection is very natural, and it is a flat ladder projection. So projection, we delete the rightmost leaf. So what is the converse? If I have a tree S and I want to take something in its fibers, then I just have to attach the rightmost leaf somewhere along the right branch, right? And I encode where I attach it by the number of nodes that are below the node where I attach. Okay, so I attach somewhere in along this right branch on one of these edges. And if I have, for example, if I attach here, I get this one. I have 2 nodes below where I attach, so I call it S2, S insert 2. Okay. It is a ladder projection. Maybe we just check 2, which is the important thing. So it is clearly, the fiber is clearly a chain. You start by attaching on top of this right branch, and you go slowly down. And the transport in this case is trivial. This is even easier than the weak order. I claim, and it's not difficult to prove by induction, that the transport, if you want to transport something in the fiber of S from S to S prime, you look at where you attach the right leaf in S, and you attach it exactly at the same place in S prime. Okay. In particular, just by the formula, the transport is clearly flat. Okay, so here there is even nothing to do. These arguments that I was saying, you push someone and so on, you don't even have to do that here. So, and it is reminiscent from the fact that the cubical realization of Hung and Tamari is actually very nice. So here we prove that the Tamari lattice is a lattice without quotient. Just prove it directly with this flat ladder projection. Okay, so I'm not sure how much you're convinced that the technique is powerful. Maybe what I do is that I take more recent posets now. So I will speak about two of them. First are framing lattices. So let me give you a crash course on framing lattices. So I start with a frame graph, gamma. What is a frame graph? It's a directed acyclic graph. And at each vertex, you have a total order on the incoming edges and a total order on the outgoing edges. And I use some conventions which are standard. So my graph is oriented from left to right, so I don't need to write orientation. And I draw my graph so that at each vertex, the incoming edges appear in order on the left, and the outgoing edges appear in order on the right. Okay, now the left corner in such a graph is a pair of two consecutive incoming arcs at the vertex, so this is the left corner. And the route is a directed path from a left corner to a sink. Okay, and we say that two routes are incoherent if they share a subpath and cross along this subpath. So rho enters from above and leaves below rho prime. Okay, so for example, these two are incoherent because they share this subpath, the subpath with one node, and you see that they cross at that node. Okay, this as well. Maybe I put this picture to show you that when you have a left corner, then both edges count. So here you really have the crossing between red and green. And these two are coherent. So for example, here they share something, but they don't cross here. Here maybe it gives the impression that it crossed, but just a picture which makes it this impression, just because of my convention of drawing. But they don't share anything, so there's no vertex. Okay. Now a clique is a maximal collection of pairwise coherent roots. You will have one root for each left corner. And these objects are studied because they encode simplices in the decay K triangulation of the flow polytope of gamma. We don't need geometry at all, so I just pass on. Okay, and you have a way to orient, or to put a poset structure on this cliques, which is a framing poset. It's a transitive closure of clockwise rotations on cliques. So how does it work? You start from a clique and you choose a route. So here's a red. You decide to remove it and you replace it by the next route that you can that is compatible with the remaining routes. And the next one when you rotate around that vertex. Okay, so that is a good way to define it. It's the next in the sense of that one. Of that one. So this poset has been studied in particular by Bergen and Sherienko. It was proved to be a lattice recently by Van Ben and Ceballos. And here I use a presentation due to Bergen and Chenevier. Usually you don't do clicks starting from left corners, you do clicks starting from sources. Okay, it's slightly different and very important for us that they came up with this presentation. So this is the framing lattice for the graph I started from. Nice lattice. And I need a slight generalization of these framing lattices because I want to make induction. It's difficult to make induction directly on this lattice by deleting vertices and things like this. It's easier to do it the way I will present. So I start with a filter of left corner. So it means a set of left corner, which is, it's closed and they're going to the right. Okay, so it means I just remove some corners on the left. And what I call an L clique is a collection of pairwise coherent roots with left corners in L. Another way to say it is that I start from a clique with all left corners and I forget some on the left. Okay. And I define the framing poset of this frame graph gamma and set filter of left corner L as a transitive closure of the rotations on L cliques. So that is the same as before, just I forget some of the routes. Okay, and now I pretend that if you have a filter N of left corners and take a minimal corner in this filter and remove it, Remove it means you just delete the roots with corner L, then you get the flat ladder projection. Okay, so here you see same picture as usual. So for example, here you see that passing from here to here, like this. Horizontal lines correspond to deleting red. Okay, and then as you same color. Okay, so here's a proof that it is a flat ladder projection. Main part of the fact that it's a ladder projection is that the fiber is a chain. The reason is because the routes, the L routes, which are compatible with given L minus L click, are totally ordered at that vertex. Okay, so this is a chain, and the transport is essentially an upper L. Okay, so transport you can define and prove the transport, and the proof that it is flat is literally 10 lines. I cheated here a little bit because I did not include the sandwich lemma. Okay, but it's really something easy to do. And in particular, by induction, we proved that the framing lattice of any frame graph is a lattice. Okay, so this was included in this written paper by Von Bell and Ceballos. Maybe I should comment. I should have commented from the beginning. These techniques that we use has nothing to do with any property of the lattice. So in particular, when your lattice is nice, let's say polygonal, semi-distributive, congruence normal, congruence uniform, I cannot prove it at the moment using this technique. Okay, so it's good and bad. It means if I start from a crap lattice, I can still prove that it's a lattice. But if I have a nice lattice, then I don't have the nice properties. And in particular, most of their papers actually could prove that it's nice lattice. So it's not that we replace this paper, we just do the lattice part. Okay, so next example are operahedron lattices. So again, a crash course on operahedra. So I start from a rooted plane tree T, and I call nest a non-empty connected subsets of nodes of T, so this kind of thing. And the nesting is a collection of pairwise nested and disjoint nests. So this is not a nesting, it's neither pairwise or neither disjoint or nested, but this is a nesting. And I will only consider inclusion maximal nestings. And in the picture, I omit singletons, which are compatible with everything. I also omit T, which is compatible with everything. Okay, just for clarity. So again, it has connection with geometry. So it's the nestings of a tree are the tubings of the line graph of T. So the poset that I will present is the poset on the graph associated with the line graph of T. And it's also a special case of poset associated graph connection. Okay, so what is the operahedron? It's a poset on maximal nestings obtained by transitive closure of the following transformations. So you start from a nesting and you flip one nest, you transform one nest of this nesting into another nest. And there are two options. So here I flip pink into green. And the first option is that the nests that I exchange have the same roots. Okay, so roots have the same minimal vertex. In this case, I orient my flip in this direction because if I look at the vertices which are in pink but not in green, they are to the left of the vertices which are in green but not in pink. Okay. I can always orient this way. And the other option is that the two exchange nests have distinct roots. And in this case, I orient the flip from the nest whose root is above to the nest whose root is below. Okay. So this is the definition of the operahedron. It's a directed skeleton of the graph associated on the line graph. So here is the graph the operahedron of the tree we started from, and here are the two flips that we saw just before. Okay, examples. Yes.
Why is it called operahedron?
Because of Lafont-Lafontaine. So it has some relation with categories here. Yeah, operas. We had a very good reason for. So examples of operahedra. The recorder is operahedron of the cloud graph, and the Danae lattice is the operahedron of the path graph. Okay. And we have seen that for the recorder and for the Danae lattice, we have this flat ladder projections. So you can try to do the same thing, and indeed the same thing works. So the projection is the following. I start from my tree T, and I will erase the rightmost leaf, which I call M. Okay. When I erase a leaf, I also just if this leaf is in a given nest, and I just erase it from this nest. That's it. I keep the nest without this. Okay. So, for example, these two things, if you erase this leaf here, you should see the same thing. Remember that I don't draw the full tree, which is maybe a little bit difficult to see here. Okay, so I claim that this is a flat ladder projection. Let me go faster because I'm slightly late. So I call n the rightmost leaf. I call I the unique neighbor of n. Projection is the one I just said. So you take a nesting, and in each of its nests, you just delete n. And then I can just explain you what is a fiber. You start from a nesting M of T minus n, and what you want to do, you want to take one of these nests that contain I and blow it up. Okay, so you have to choose one of these nests and blow it, and it forms a chain because the nests containing a given vertex are nested. Okay, so it forms a chain, and so this is the reason why it's a ladder projection. And you can express the transport in a very simple way. And here I have to admit that we prove that it is flat. We really need some technical lemmas where we really suffered on. Still, it's 1.5 pages. Okay. To be compared with this very nice paper. This paper is super original. They proved that the parahedron is a lattice, introducing the ornamentation lattices, and they also discuss why it's semi-distributive, so they do much more than what we do. But still, the proof here is really easy. Okay, questions? Yes?
Is there any generalization for general tubings with general graphs?
I come to them.
Okay.
Okay, so more applications. So now what I will do will even go faster than what I did so far. What I will do is that I will flash just one slide for each application that I can think of. Okay, so if you don't know the lattice I will speak about, you can just wait for one slide and you get the next chance. The next slide. So first application is poset of regions of supersolvable arrangements. So here, a supersolvable arrangement is an arrangement which you can decompose into the red and the blue hyperplanes. The red have to be a current one supersolvable arrangement. The blue have to have the properties that when you intersect two of them, the intersection is also in the red. Okay, now I claim that if you forget the blues, then you get the ladder projection, because in a given red region, what you see is a chain. Okay. And this ladder projection is flat. And actually, if you really read this proof, it's almost what they do. Not completely, because they use global comparison. So it's slightly different. Actually, when I read against their proof, I was like, they already did exactly the same, but I think not exactly. Okay, next one, permutry lattices. So permutries are generalization of permutations and binary trees. So it's trees with local conditions around each vertex. And here you have a natural projection map, which is delete the rightmost vertex and maybe just reconnect. If you disconnected the graph, you just reconnect it. Okay, this is exactly the same thing as what we did for the permutahedron. We deleted the last number, so it's a rightmost leaf in the corresponding permutry. And for the associahedron, we deleted the rightmost leaf, but it's the same as thinking that you delete the rightmost node. Okay, so this is also flat ladder projection. Next one, Nathan's rectangulation lattices. They come in two flavors, either the weak rectangulations or the strong ones. So here, the natural projection map is to delete the rectangle containing the bottom right corner, so it's in red in my pictures. So by delete, I mean if your rectangle looks like this, then you push its left border to the right. And if your rectangle looks like this, then you push its top border to the bottom. Okay, this is a flat ladder projection in both cases. Next one, interval hypergraphic lattices. I suffered about 2 years ago to prove the lattice property of these things. Well, it's not a very difficult proof, but I had to invent these quasi-lattice quotient maps. It is there's a clear projection, which is you delete the inclusion maxima at upper edge. And this is a flat ladder projection. Next one, non-kissing lattices of gentle quivers. Here it's slightly more complicated. I actually don't have the full proof, but I believe that deleting a source vertex is always a flat ladder projection. The source vertex, you might ask, what's the source vertex here? This is a source vertex because there are some relations that I didn't speak of. Okay. And now we come to the real reason why we invented this technique. It's a permutoassociahedron. So permutoassociahedron was produced combinatorially by Kapranov and realized as a polytope by Reiner and Ziegler and revisited by Castillo and Liu. So it's a polytope which is a mix between the permutahedron and the associahedron. The elements of the lattice of the vertices of the polytopes are bracketed permutations. Okay. I don't enter the details, but well, there is a geometricalization. There's something slightly disappointing is that whatever direction you choose to orient this polytope, so you get a poset, but this poset is not a lattice. Never. Whatever the direction you take in dimension 3 already, it fails to be a lattice. But with Dasha, the last 2 years almost, we managed to find another orientation of this graph, which seems to be a lattice. And we really tried really hard to prove that it was a lattice using the BZ lemma. The problem is that we don't know global comparison in this lattice. We have no way to tell you global comparison. We define our orientation locally. But we can prove that it is a flat ladder projection. Okay. Questions? No? So now we try to go industrial and go to scaffolding projections. So that's a big version of ladder projections. So here I have the same statement as this one, except some little changes. So the main part is that instead of assuming that the fibers are chains, I assume that the fibers are joint semi-lattices. Okay, so the fiber above each element Q is a joint semi-lattice whose joint I denote by joint Q. At the top, I still have a top element which I still denote by TQ. And the next change is that it's much more demanding to be flat. So the first thing is that we define here the transport map as well. You go the fastest you can from Q to Q prime. So you start at P and go the fastest you can to the fiber of Q prime. Here we have to assume that it exists. That there is. So because we had a chain, we could just take the minimum here, but there we have to assume that there is a linked element in this set. Then we also have to assume that this transport behaves properly with respect to the fiber joints. Okay. That's an additional assumption. And we still have to assume that the transport behaves properly with respect to chains. Okay, and in this case, we have the same result. That if we have a flat scaffolding projection and Q is a joint semi-lattice, then P will be a joint semi-lattice. The description of the joint is the same as before, except now instead of taking a max, I take the joint in the fiber. Okay. Same as slightly different. Okay. So applications of that. The first application to play with is type D recorder. So type D recorder, we have sign permutations with an even number of signs. So instead of writing -1, I write 1 with a bar on top. Okay. And we have 2 kinds of correlations. The first one is that if A is more than B, then I can exchange A and B. So A is more than B, it can also have signs. So for example, -1 is more than 3. Okay. And the second kind of correlation is that if I see at the beginning AB and A is bigger than -B, then I can exchange A and B and put a sign on both of them. Okay, or change the sign of both of them. That's the type B recorder. And again, we have a natural projection map from the type Dn recorder to type Dn-1 recorder, which consists in if you see n, you delete n. It doesn't change the number of negative minus signs. If you see -n, then you delete n and change the first sign. Okay, so that's at least you stay in the n-1. And I coded as usual the correlation. So for example, here this edge is coded red because if I delete 3, then I see the same thing at the 2 endpoints. And maybe I should take that example. This is also colored red, because if I delete red, I see the same thing. I hope you see the same thing. I see 1 bar, 2 bar here. And I also see 1 bar, 2 bar here, because here I delete 3 bars. So I put a bar on 1. Okay. Okay. So I claim that this is a flat scaffolding projection. So what is the deletion? We just explained what is the projection, deletion of n or deletion of n bar. Should be n bar here, sorry. What is a fiber? Well, you start from a given permutation tau. What you can do is just put n wherever you want with this part. Or you can put n bar wherever you want and change the first sign. Okay? And well, put n wherever you want is clearly a chain. Put n bar wherever you want is clearly a chain. But these two chains are related by this weird diamond. Okay? So it's essentially a path, except you have this little diamond in the middle. So it is a scaffolding projection. We just explained that the fibers are single diamond chain. The rest is automatically projected. And the transport is essentially the same as the one we discussed for the weak order in type A. Essentially, n get pushed to the left, except you have to be careful what happens when you pass the diamond. So this is essentially the same proof. We'll do the same meanings here. Okay, so in particular, we proved that type Tn weak order is a lattice. It's maybe not the best proof for the end, but it's good to play it. Okay, so now why did I really wanted this scaffolding projections? Because of this shoot move lattice on pipe dreams. So we have seen pipe dreams a lot during the week. So pipe dream for me is a filling of the triangular shape with cross ties and bump ties. So it defines some pipes which go from the left of the triangular shape to the top. I label these pipes from 1 to 6 on the left, and then it gives me a certain permutation on top. I assume that the pipes cross at most once, so pipe dream is reduced. And I denote by PD of W the set of pipe dreams with a given permutation W on top. Okay. And now there is a natural, there are several transformations on pipe dreams, but in particular there is this shoot move transformation. It works as follows: you take a rectangle in the triangular shape, and if it turns out that you have only crossings in this rectangle, except at the bottom left corner, the bottom right corner, and the top left corner, then you can exchange the bump tile in the bottom left corner with a cross tile in the top right corner. This is called the shoot move. It was conjectured to be a lattice in 2012 by Rubé, and about a year ago, 2 papers proved it the same time. I have to admit that I have not really read a lot this one. I know that this one they prove it using the BZ lemma. So this is the shoot move lattice on the example I chose. So it's a bit complicated, but still. And I claim that there is natural projection map from pipe dreams of 1.6 to pipe dreams of 1.5, which consists in erasing or shrinking pipe 6. Okay, so I look at pipe 6, I color all triangles where it passes, and I just shrink this ribbon. And I obtain a pipe dream on 5 with a scar. Okay, I remember the scar, it helps me to see. What is a scar? It's a path starting at the vertex, arriving at the position where 6 was, W minus 1 of n. It has vertical steps and diagonal steps, and the diagonal steps, they must pass through bump ties. Okay. So that's a scar. In particular, the dominance order on scars is clearly a distributive lattice. Clearly means you have to think 2 minutes. The reason is if you take 2 scars, and it takes the upper hull of these 2 scars into the joint. The bottommost scar is this scar, the lower hull of the first omega minus 1 of n columns, and the topmost scar is the lower hull of the diagonals of the bump tiles. of the pipes which finish to the left of it. Okay, so you can describe it. I mean, it's really explicit. Okay, so now here is my main proposition. The deletion of pipe N is a flat ladder projection. Again, I call it according to which is the last pipe you have to delete so that you see the same thing. Okay. Okay, so
Sorry, the ladder projection or scaffolding?
oh, sorry, that's a bad copy paste. This is a scaffolding projection. Thank you so much. The reason is that the fibers are not chains. There are these weird, these dominance orders on scars. Thank you so much. So there's a typo everywhere. It's not ladder. It's scaffolding everywhere. It's the section. So the fact that it's scaffolding, the main part is the second point, which well, I just said it. The fibers are these dominance lattices on scars. And the fact that it is flat is slightly more complicated. I have to define a certain statistic on my scars and prove that transport is given by, so if I have a given scar and I transport it to the lowest scar with a given property on my statistic. Okay, it's independent of the path where I pass from. Okay, and I have to say that I need a few more lemmas that are not yet written. I have to admit that this is not completely finished, but we checked and it seems to be completely correct. Okay, one more. Oh yeah, so in particular, by induction, we prove this, that the should move poset is a lattice. Again, there is much more in these two papers, and this is one I know it better. Okay, but it's a quick way to. Okay. One more example. There's a recent paper, I think end of last year, which proves that the oriented skeleton of the cyclohedron, seen as the graph as the cyclohedron as the site of the cycle, is a lattice. And here again, there is a very simple scaffolding projection, which consists in cutting the edge from 1 to n in the cycle. And you obtain a projection from the cyclohedron to the cyclohedron, which is flat and scaffolded. Okay, and well, next application is yours. I would really like to know about lattices that you know and believe they could be such projections. I'm very interested to know, so please send me an email or come to discuss. Out of time, I have one slide about the use of AI in this work, so I think it's good to mention when you use and how you use it. So in particular, we used it, so Dasha used it to arrive to the concept of flat ladder projection. So we discussed about this kind of projection since 2 years, but she really used it to arrive to a nice notion on this. And we used it to prove some lemma, but I also really needed to forget it to manage to prove other things. The images were generated by AI. I really tried to understand the ecological constants of this work. It's really difficult so far. At least for the images, it told me that it will only cost the same energy as a lamp during 4 hours. So pictures of the titles that are clearly generated by AI, I think the cost compared to my trip to the US. Okay, thank you very much.
Any questions or comments for Vincent?
So if you have a flat ladder projection, you always have to draw these pictures like in a coordinatized way. Do you get canonical coordinate systems from flat ladder projection?
No, so it's sort of in the other direction. Like this cubical realizations give me automatically ladder projections. In the other direction, it's not completely clear. This is completely combinatorial. I don't need coordinate, doesn't give me coordinate, or at least I don't really know how to get coordinate from that.
And can you do this for Cambrian lattices beyond type A with the Fermi-trees?
I haven't tried yet. That's a good question. So this is one of your lattices, and it's also my lattice, I guess, or it's named like this, but this is this kind of emails that I want to receive.
Nathan.
So, in every one of your examples that were either simple or familiar enough for me to think this through, it seemed like the projection map, a posteriori, once you know that the big thing is a lattice, the projection map needs to be a lattice. Is there a theorem there, or do you know that, you know, examples where it's not?
I'm not sure I have to say that. I forgot to say because of you that you saw that I have a lot of projections in lattice quotients of the weak order, and I think there is also a theorem which says that you have a natural projection map from any lattice quotient of the weak order on n element to the weak order on n-1 element by just deleting the arcs incident to n. And I think this will be always flat, but I haven't had time to work it out. Yes.
What about a non-crossing partition lattice?
Thank
Is it
you.
easy or too hard?
I don't know. Please send me an email. I have to think about that. I have to come up with a projection. So here is where the originality is at the end. So you have to look at your lattice, look whether you can find a projection which makes sense, and then you have to prove it. Like usually what we do is that we guess transport and prove that it is flat. And also forget to say that if your lattice is polygonal, well, you don't know yet that it's a lattice, but if what you want to arrive to is a polygonal lattice, then you try to understand this, that the transport composes along paths. You can, of course, do it only on two faces. So, for example, for the permutoissociahedrons, this is our current proof. It is slightly cheating because we don't really know that it is polygonal. We have a long proof that it's polygonal, and then we just use the polygons. So, for example, when Dasha presented this way, she showed that the weak order was a lattice by just checking bread relations, that it transports correctly on bread relations.
Any other questions? One more.
So,
It's a quick one.
exactly, a couple of
Yeah, this is-
Okay, let's thank Vincent again.